Hello and welcome to Mr. CFD. In this training video, I would like to describe a project named Solar Collector with FMHPA CFD simulation. As you know, we did this project in ANSYS Fluent. First, search for Fluent in the Windows search bar. Click on Fluent, and in the launcher, select Double Precision and 3D because our geometry is three-dimensional. Here, we select the number of cores in our system that we want to use. We are using 28 cores. Finally, click on Start. After reading the mesh into Fluent, we want to view key information about the geometry and mesh. I navigate to the Domain tab, Info, where the console displays the number of cells generated, approximately 150,000 cells in total. In general, I click on Scale and you can see the scale of the project, which shows the minimum and maximum values in the X, Y, and Z directions. Next, I click on Check, and the software shows several important mesh quality metrics. The most critical parameter is the minimum volume, which must be positive. If this number is negative, our mesh is invalid. Additionally, we have to see Done in the console. I then click on Report Quality, where the software provides more detailed information about the mesh. The most important metric here is the minimum orthogonal quality, which should be greater than 0.1. Our minimum orthogonal quality is 0.18, indicating our mesh is acceptable for this project. Moving on, I click on Display to view the boundary conditions. For example, I select Inlet, click on Display, and in the graphics window, you can see the inlet boundary highlighted. When I select Outlet and zoom out, you can see the outlet of the domain. After that, I select all outlets and click Display. Scrolling down, I select all the walls, click on Display, and you can see all boundary conditions highlighted in the graphics window. In the solver settings, I use pressure-based because our Mach number is less than 0.4. Time dependency doesn't impact our simulations, so I've used steady state. For gravity, since body forces impact our simulations, I activate this option and use -6.867 in the Y and Z direction. This value comes from simulating the project with a 45-degree tilt, multiplying cos 45 degrees, by 9.8 meters per second gives us 6.867. These settings simulate the project as you see it in the graphics window. Next, I expand models and activate the energy equation. For viscous effects, I use the K-epsilon model. This is appropriate for our application as it provides good accuracy for fully turbulent flows while being computationally efficient. For radiation, we don't use any specific model but activate the solar load model, solar ray tracing. For materials, Fluent uses air by default. Opening this, we can see the properties such as density, specific heat, and thermal conductivity. To add another fluid or solid, you can select from the Fluent database, choose Fluid or Solid, then select Material from here. Then click Copy. Besides, you can modify properties as needed and change the name and insert chemical formula. In cell zone conditions, you will see that the type is fluid. I will open this zone and confirm its type with the air type. All fluid regions are set up similarly. For solid zones, aluminum is set as the material, with all solid zones configured identically. For boundary conditions, I select Inlet where the type is set to mass flow rate. Clicking Edit, I can specify the mass flow rate and direction, -z. In the Thermal tab, the temperature is set to 126.2 degrees Celsius. For the outlet, I use pressure outlet with 0 gauge pressure and a thermal backflow temperature of 115.8 degrees Celsius. All other outlets are configured similarly. I select the first wall and click on Edit. In the solution methods, I use the coupled algorithm for pressure-velocity coupling, which provides better accuracy for complex simulations despite higher computational cost. For spatial discretization, I use least squares cell-based for gradient, second order for pressure, second order upwind for momentum and energy, and first order upwind for turbulence parameters. Here we can see the under-relaxation factors, which we can reduce when we have an unstable solution. Under residual monitors, all equations are set to solve with convergence criteria of 0.001, except for energy, which is set to 1e6 due to its importance in this thermal simulation. The solver will stop when all equations achieve these convergence values, meaning the difference between the last two iterations is less than these thresholds. For initialization, I use hybrid initialization. And for run calculation, I set the timescale factor to 1 and specify the number of iterations before clicking Calculate. To analyze results, I create planes for visualization. Under Domain, I create planes such as a YZ, ZX constant plane, and an XY plane. In results, I can display various contours such as pressure, velocity, and most importantly for this project, temperature. We navigate to the Reports section and select Surface Integrals. For example, if we want to know the area of the inlet, we select Inlet from the Surfaces list and click on Compute. The software then displays the area of the inlet in the console. Next, I change the report type from Area to Area Weighted Average. Let's say I want to know the average pressure at the inlet. I select Pressure from the Field Variable dropdown, keep Inlet selected, and click on Compute. The software now shows the area-weighted average pressure at the inlet. We can easily change the variable using the drop-down menu or select different boundary conditions from the surfaces list to analyze other parts of our model. Moving on to volume integrals, this allows us to analyze properties within 3D zones rather than just at boundaries. For example, if I want to know the volume average pressure in a specific zone, I select Volume Weighted Average as the report type, choose Pressure as the field variable, select the desired zone from the Cell Zones list, and click on Compute. The software then calculates and displays the volume average pressure in that zone.
I hope this video is helpful for you. To benefit from Mr. CFD services, including simulation, consultation, and training, visit our website, www.mester-cfd.com. Contact us via info@signmester-cfd.com.